We have already seen this setup. X has density little f, h is a function R to R which is a bijection, and inverse is differentiable, and we are transforming x using this function h to get y equal to h of x. Then the density of y is given by gy, which is f of h inverse y, then this term. Now we plan to generalize this to multivariate setup where this x will be a random vector. This will have a joint density, so I will put an arrow on top of it. So this h will be also from some Rn to Rn. H inverse still makes sense, bijection still makes sense. The first question is what is meant by this, and the second question is when I take this, then y has density equal to gy. This is meaningful, but what is meant by this? So these are the 2 points which needs to be taken care of when we generalize the one-dimensional Jacobian formula to multivariate setup. Let's start with the univariate setup first. Suppose I have a function f R to R which is differentiable at a. By this we mean limit as x goes to a, fx minus fa by x minus a equals, I have called it m, that is finite. So the main news is that it is finite. And if I call it m, this m is called the derivative of f at a. Now just turning things around, we can write it as fx minus fa plus, this entire thing should be inside braces, fx minus, I am subtracting this fa plus m times x minus a, the whole thing divided by x minus a is 0, and we have already discussed the geometric significance of that. This is the equation of a straight line passing through the point a comma fa having slope m, and this says that this straight line approximates this function very nicely at the point x equal to a. Now we can use this to generalize differentiability to arbitrary order. Suppose this is from Rn to Rm. In that case, this we do not try to make sense of. This is only for one-dimensional case. We will directly attack this. So we will say it is an x vector converging to a vector, which makes sense, that is their distance goes to 0. Denominator also we do the same thing, we are taking their distance. This distance is taken in Rn, the usual Euclidean distance. Now this is a vector because this is in Rm, that's a vector. In this case, this is a vector, this I will replace by a matrix. In other words, we are trying to approximate fx locally at the point A by a linear transformation. So if you change x a little bit from A, so you are moved by this amount, then the amount of change in the function is m times that thing. So if you can take time to just think about it, it's not an entirely obvious concept, but you should see that it is a direct imitation of the one-dimensional case. So we shall say if such a matrix M exists, the order of this M has to be M cross N. If such a matrix exists, then we shall say that the function f is differentiable at the point A and the derivative is the matrix M cross N. Now, this result that we had in one dimension had the extra advantage that you could directly compute this M. But here this M occurs inside. If such a matrix M exists, how can you find such a matrix M? That is not entirely apparent from this expression, but here it was very easy. M equals something. So can we have something analogous like this? The answer is yes. Let me explain through an example. Suppose I have taken n and m both equal to 2. So I have f x1 comma x2. Now I need to get a two-dimensional vector as the output, which means my f has got two components. I will call this one f1 and this function f2. These are the two component functions of f. So f1 is a function from R2 to R, and similarly for f2. Now I can write down this m like this. Mij, that is the entry of m, row I column j, is del fi del xj. So you are differentiating partially the ith component by the jth variable. Just remember, I occurs upstairs, j occurs downstairs. If you do not do that, in that case it will not be m cross n, it will become n cross m if you swap them. Now why this occurs is something that we do not need to worry about right now. You will see the proof later. The proof is quite straightforward, but let's just do the computation in order to appreciate it. The first entry, 1/1 entry, is obtained by partially differentiating this one, x1, x2, with respect to x1. So x2 behaves as a constant and you get x2. Similarly, when you take the same thing and differentiate it with respect to x2, you get this entry, which is x1. For this row, you have to work with this component. Differentiate it partially with respect to x1, you will get 1. And differentiate it partially with respect to x2, you get minus twice x2. And that will be the derivative matrix at that point, x1 comma x2. Now this is what is called the Jacobian matrix. Now notice, in this case we get a square matrix because we worked with m and n equal. In general it is not a square matrix. But if it is a square matrix like this, then we can also compute its determinant, which has some geometric interpretation, and that determinant is going to play an important role in the multivariate Jacobian formula for transformation of distributions. In this problem, I give you a function R2 to R2, and your job is to find Jacobian of H. And also find the determinant of the Jacobian.